Okay, so welcome back to MOPA. Today we have Rasmus Blanck from University of Gothenburg. Rasmus is a senior lecturer in logic and theoretical philosophy there. He received his PhD in 2017. I believe under Ali Inayat, is that right?
That's right.
Okay, we're really excited to have him here. This is his first time at MOPA, so welcome, Rasmus.
Thank you so much. Thank you very much for the invitation. It's great I couldn't think of a better place to be discussing my work. So thank you for that, and thank you all for coming. So today I will be talking on, the topic is the same as the topic of a recent paper of mine in the RSL. I won't be telling exactly the same story as I tell in the paper. The paper is there if you want to read it, but I will try to focus on the spine or the backbone of what's going on here. But the topic is different kinds of incompleteness results for arithmetically definable extensions of, let's call them strong fragments. I think Roman used to call them strong fragments of PA. So there's a threefold purpose of what I did in the paper and what I'm going to present today. So I want to generalize these different kinds of incompleteness results to sigma n definable theories rather than the ordinary RE theories. And at the same time, I want to push the base theory as far down as it will go below PA. Looking into how strong fragments do I need to prove these results for sigma n definable theories. And hopefully at the same time make some kind of contribution to the bigger picture here. Trying to find a smallish collection of general principles that can be used to prove these results that hopefully make some kind of sense and hopefully have some likeness to the ordinary principles that we use when we prove incompleteness results. You might wonder why I want to do this. One reason is that as I was writing up my thesis, working with Ali, as pointed out, there were two papers in circulation at the time, one by Taishi Kurahashi and Kikuchi, and another one by Salehi and Siraji, where they both generalize Gödel's incompleteness, the first incompleteness theorem, to sigma n definable theories. And Ali and I were working on generalizing by then well-discussed result by Woodin on the universal algorithm. I think that Vika has given a talk about this in this seminar earlier. Perhaps also Joel Hamkins has made a great effort in popularizing Woodin's result through his blog. So we were working on that, and that is in a strong sense an incompleteness result. And as these papers by Kurahashi and Kikuchi and Salehi and Siraji appeared, I thought that, well, I can do better. I can prove stronger incompleteness results for sigma n definable theories, and I can miniaturize them to fragments of PA. So that's one kind of motivation for doing this, and also since I wanted to work out the details. So many of the results in my paper are really just proved by doing the same thing as we usually do, while carefully keeping book of what's going on. So I won't be presenting too many proofs. You will have to trust me on what I say in many cases, or simply have a look at the paper. So let's get into some more detail at least. So what kind of results am I talking about here? I'm talking, for example, about Gödel's first incompleteness theorem, which I phrase in this way here. There is a true pi1 sentence that is not provable by PA. Okay, so that's one kind of result that we want to generalize. Another kind would be, well, con of PA is not provable in PA. And I will, rather than, showing you the exact results that I have in my paper, I will stick to these things that relate to consistency statements, because I think that will make the picture more clear. So this is a different story than the one I told in the paper. Another kind of result that we want to generalize is the fact that not con of PA is pi1 conservative over PA. And just to remind you, I guess that everyone knows this already, but pi1 conservativity means that if a pi1 sentence is provable in PA plus not con PA, then PA already proves this pi1 sentence. And finally, yet another kind of result here. So you have to forgive me about this Gaspari reference. Maybe one of you could enlighten me later. But the fact that every model of PA has an end extension to a model of PA plus not con PA. Of course, Pfefferman proved that PA plus not con PA is interpretable in PA. And we have the Ori-Hayek characterization of interpretability. But the only, the earliest proof I could find that gives me this is in Gaspari's paper on partial conservativity. So please, if you have a better reference, let me know after the talk. The Gaspari will be the label for this kind of result throughout this talk. Okay, so I'm going to generalize these four results to sigma indefinable theories while restricting PA as far as I can. And how far is that? How far down will the base theory go? That depends on which of these results we consider. So if we look at sigma n plus 1 definable theories with n restricted to be greater than or equal to 0, some classes of theories emerge. In my abstract, I say that 2 salient classes of theories emerge, but well, maybe 3, maybe more, who knows, at least 3. So to generalize Gödel's first to sigma n plus 1 definable theories, it suffices to have a sigma n sound extension of I sigma n plus exp. So that's one class of theory that we will be considering. If we want to prove Gödel's second or this result by Kreisel, if we want to generalize them in the same manner, it seems that we need something more. We need pi n complete consistent extensions of I sigma n plus exp. And we will see later precisely where we use these extra assumptions in the proofs. And if we want to go the full way to construct end extensions of the kind that Gaspari does in his paper, we also need pi n completeness of the base theory, but we have to bump it up to I sigma n plus 1. It doesn't suffice with I sigma n plus exp anymore. So we need a little more induction. When I say need, I really mean the proofs I know of, they use I sigma n plus 1, but if you know of a more clever proof, please let me know. So that's a very short summary of what's going on. What about the kinds of principles I was talking about that I want to use to prove these kinds of results? Well, so one thing that we need to settle is how to represent sigma n plus 1 definable sets. Because if we have sigma n plus 1 definable theory, the set of theorems provable from that theory is going to be sigma n plus 1 definable, and their PA won't cut. And we will see that later as well. We also want to define what I call strong provability predicates. There are many different names of those in the literature: oracle provability, or N provability, and some other terms as well. So I want to show some of these properties of, I'm going to define what strong probability would mean here. We need a suitable generalization of Leb's theorem to this sigma n plus 1 definable setting. And I'm also going to employ a generalization of the Ori-Hayek characterization, not of interpretability here, since we're in a finitely axiomatizable setting. So we won't get interpretability as an equivalent of the ordinary equivalence in the Ori-Hayek, but we will use pi n conservativity instead. So this is the Ori-Hayek characterization of partial conservativity rather than of interpretability. Okay. So I'm just very briefly going to show you some, review some concepts, notation, and basic results, because I'm sure that all of you know this very well. So we define the classes sigma n and pi n of formulas in the language of arithmetic, as usual, in a way that we want. Saying that a set X is sigma n definable means that X is the set of numbers such that, there is a sigma n formula such that K is in X if and only if it's true that sigma of K. So as always, this blackboard n is a standard model of arithmetic. And I sigma n is what we used to be. It's PA with induction restricted formulas in sigma n. We're going to employ partial truth definitions for sigma n plus 1 formulas, and their most useful property can be verified in I sigma 0 plus exp. We're going to be talking about end extensions. So K is an end extension of M if all the new elements of K are greater than everything we had in M already. And we're going to be talking about the notion of pi n completeness. So a theory is pi n complete if it proves all the true pi n sentences. And conversely, T is, we could of course talk about sigma n completeness as well, but I'm going to use pi n completeness and sigma n soundness in this talk. So T is sigma n sound if every sigma n sentence T proves is true. And the sigma n theory of a model M is the set of sigma n sentences that hold in M. And these are actual sentences, real world sentences, not anything that M might believe is a sentence. And finally, we observe, as is well known, that the pi n theory of the standard model is sigma n plus 1 complete. And we observe that if, not if, but T is sigma n sound if and only if T plus the sigma n plus 1 theory of N is consistent. Okay, hopefully that is fine. So let's have another look at the first incompleteness theorem. So in one common modern formulation, we might say that if T is an RE consistent extension of PA, then there is a true pi 1 sentence pi that is not provable in T. And a few years back, as I mentioned, Kikuchi and Kurahashi, as well as Salehi and Saraji, almost simultaneously published papers proving this generalization of Gödel's first two sigma n plus 1 definable theories. And the statement here is that if T is sigma n plus 1 definable and sigma n sound, then there is a nice parallelism here. So then we have a true pi n plus 1 sentence that is not provable in T. And of course, for n equals 0 here, RE and sigma 1 definable means the same thing. Consistent and sigma 0 sound means the same thing, and we get the correct complexity of this unprovable sentence. So, I mean, the ordinary phrasing of Gödel's first fits nicely to this kind of hierarchical generalization. So when I saw these papers, I realized that, well, okay, so I know exactly how to weaken the base theory here, since I had been doing similar things. So as I mentioned in the introduction, it suffices to consider sigma n sound extensions of I sigma n plus exp. And we're only going to use exp when n is equal to 0, because we're going to be using partial truth definitions, and then we need a little bit more than I sigma 0 to do the work. Of course, as many of you know already, for partial truth definitions, we can go a little below I sigma 0 plus exp, but I prefer to keep it in this way because the hierarchical picture gets nicer. So bear with me there. So how can we prove this? Well, it's basically about realizing what we need to represent sigma n plus 1 definable sets, and that we're going to use these strong probability predicates rather than the ordinary probability predicate for our theory T. And then we basically use a similar argument as we use to prove Gödel's first today. So for the representability of sigma n plus 1 definable sets, I mean, the basic result that we want to generalize here is from Ehrenfeucht and Pfefferman, saying that, okay, so if we had a sigma 1 definable set, then that can be represented in Q already. And it can be represented in a nice way, so that K is in X if and only if T proves phi of K for this representing formula, if and only if phi of K is true. So this is what Lindström, for example, calls a correct numeration of X. And this generalizes very well. I suppose that this was known already. It should have been. Many of the results I'm going to mention today are probably known since before, but I haven't been able to find proofs of them. So please, again, if you know of proofs of the results I'm talking about, please let me know. So what it turns out is that we can represent sigma n plus 1 definable sets in pi n complete consistent extensions of I sigma n. I'm not sure why I put sigma n plus 1 definable here, because it doesn't matter. What matters is that T is pi n complete consistent and extends I sigma n. So then we can represent the sigma n plus 1 definable set with the sigma n plus 1 formula in a similar manner as the way we used to doing for RE sets in Q. So let's spend a slide on what I call strong provability. So the strong provability predicate, I mean, provability from true sigma n plus 1 formulas is defined as follows. There is a Y, which happens to be a sigma n plus 1 sentence. Sorry, I should have said sentence earlier. Probability from true sigma n plus 1 sentences. It's a sentence, it's true, and T together with it proves X. This is a strong probability. And we should, as always, be careful when I write PRT as the provability predicate of T, I should be more careful in what is the choice of representing formula here. I mean, how do I represent the axioms of T? We know from Pfefferman that if you choose the representing formula in a clever or an odd way, we get other kinds of results than we want. So while we're considering sigma n plus 1 definable theories, whenever I write PR of T, this is going to be based on the pi n binumeration of the axioms of T in the base theory I sigma n plus the true pi n sentences. And as long as we're restricted to those kinds of numerations, everything should be fine. But it's important to keep that in mind, and it's also something that I had to check, that sigma n plus 1 definable theories can actually be binumerated by pi n formulas in this theory. So let's keep this at the back of our heads. So this is a representation of the property of being provable in T from true sigma n plus 1 sentences. So we can think of this formula as representing the sigma n plus 1 definable set, which is the set of sentences provable from T plus the true sigma n plus 1 sentences, representing in pi n complete consistent extensions of I sigma n plus exp. Okay, let's also remember what a consistency statement means here. So, as we all know. So we're ready to prove the generalization of Gödel's first. So let's take T to be a sigma n plus 1 definable and sigma n sound extension of I sigma n plus exp. Use the diagonal lemma to construct a pi n plus 1 sentence gamma that is equivalent to it not being provable in T from true sigma n plus 1 sentences. Then the proof is more or less the same as the ordinary proof of Gödel's first would run, with a slight variation. So since T is sigma n sound, T plus the sigma n plus 1 theory of n is consistent. So let's suppose that gamma is provable in this extension of T, which we know is consistent. Then, since we can represent sigma n plus 1 definable sets in this theory, we have that the theory proves that gamma is provable from true sigma n plus 1 sentences. Okay, but by construction of gamma, we get a contradiction. Okay, so this is more or less as usual, except that we go through this extension of T rather than assuming gamma to be provable in T simply. So gamma couldn't be provable in this extension of T, so it can't be provable in T. And by construction of gamma again, the sentence not provable in T plus sigma n plus 1 sentences of gamma is unprovable in T. But that sentence is true. So this is an example of a true but T unprovable pi n plus 1 sentence. But this sentence need not be T provably equivalent to the consistency statement. I mean, this strong consistency statement. For that, we need a little bit more. But we get an example of a true but T unprovable pi n plus 1 sentence by simply setting the stage in a good way. Okay, so let's move on. Let's look for a moment on partial conservativity. So Kreisel showed that if we have an RE consistent extension of PA, then the negation of the consistency statement of T is pi1 conservative over T. And a generalization to sigma n plus 1 definable theories looks like this. So if we consider sigma n plus 1 definable pi n complete consistent extensions of I sigma n plus exp, then we can show that the inconsistency statement is pi n plus 1 conservative over T. So this follows from one of the results in my paper. There's also a related result in a recent preprint by Kurahashi and Albert and some others. And the proof I'm going to show is more or less taken from their paper because it's a lot shorter and nice for the purpose of this talk. Now the main ingredient here is Loeb's theorem in the sigma n plus 1 definable setting. So we note that Loeb's derivability conditions hold for the strong provability predicates. And the only thing that matters a bit is that the base theory here is sigma I sigma n plus exp plus the true pi n sentences. And these closure conditions can be verified in weaker theories, but we need some more truth from the standard model to be able to verify this. Once we have done that, the ordinary proof of Loeb's theorem goes through with the required modifications. So over this base theory again, I sigma n plus x plus the true pi n sentences, we get what we want for these strong probability predicates. So now we can show that the negation of the strong consistency statement is pi n plus 1 conservative over T. So let's take pi n plus 1 sentence that is provable in T plus this inconsistency statement. And if we put that in contrapositive form and expand the definition of the consistency statement, we get this implication. And we note that since not pi is a sigma n plus 1 sentence, T proves that not pi is a true sigma n plus 1 sentence. And then it's easy to see that this means that not pi implies that it's not provable in T from not pi, that something false. So contrapositioning this again, we get the left-hand side of Loeb's theorem, and this is where we actually use pi n completeness. So pi was provable in T already. Yeah, so this proof is borrowed from the paper I mentioned by Kurahashi et al. Okay, so that's nice. And now we can also, using this formulation of Loeb's theorem, we can also show Gödel's second by the ordinary proof that the consistency statement is equivalent to gamma not being provable in T from the true sigma n plus 1 sentences over this base theory I sigma n plus x plus the true pi n sentences. Okay, very good. So let's move on to the even more interesting things, perhaps, at least for the purposes of this Models of PA seminar. So another result is this generalization of what I attributed to Gaspari. But anyway, we want to show that if we have a sigma n plus 1 definable pi n complete consistent extension of I sigma n plus 1, then every countable model of t has an end extension to model of t plus the inconsistency of t plus the true sigma n plus 1 sentences. And the ingredients in this proof is first what we just shown, that we have the pi n plus 1 conservativity of this inconsistency statement over t. We're going to use a reflection principle for a version of these strong probability predicates that we've seen already. We're going to use the arithmetized completeness theorem to construct the end extensions, and we're going to use a generalization of the Ori-Hayek characterization of partial conservativity in this general setting that we're working in. In the abstract, I mentioned that I would talk a bit about the generalization of, miniaturization of the arithmetized completeness theorem, but as it turned out, I don't really need it for this proof, but I'm going to mention it anyway. But again, you could look at the paper if you came here to hear about that miniaturization. I'm sorry, I will mention it anyway. Okay, so what about these bounded strong probability predicates? So if we look at this probability predicate for t plus the true sigma n plus 1 sentences, we can rest assured that it is on the form one existential quantifier followed by a pi n formula. So we bound this y by a k and say that, what should we call it, the k probability? Maybe that's something else. But the bounded probability of from in t plus the true sigma n plus 1 sentences is, so we restrict the length of the proof, the Gödel number of the proof, and we restrict the Gödel number of any true sigma n plus 1 sentence that we might use in this proof. And this formula is pi n in I sigma n by the sigma n collection axiom. So, and the small reflection or the explicit reflection, it's got many names, says that, okay, so this base theory again, I sigma n plus x plus the true pi n sentences, verifies that if we have a short proof of phi, short meaning that it's an actual proof. Sorry, where is the quantifier? Yeah, there is the quantifier for each phi, and k being a natural number. So this base theory verifies that if there's short proof of phi, then phi holds. I think this is originally, without the sigma n plus 1 addition here due to Pfefferman in his 1960 paper. Okay, so we have these bounded probability predicates. I'm going to mention this version of the arithmetized completeness theorem. So this formulation is from a paper by McAloon, saying that if we have a model of PA and a set of sentences definable in M such that M thinks that T plus the true pi M sentences in the sense of the model M is consistent, then there's sigma M elementary end extension of M that satisfies this set of sentences T. And so for other purposes in my paper, I needed smaller version of this. And it seems that, okay, so if we're looking at sigma n plus 1 definable theories again, I mean, if we restrict ourselves in this sense to theories that are sigma n plus 1 definable in M, and M is a model of I sigma n plus 1, and M believes that T plus the true pi M sentences in the sense of M are consistent, then there's a nice sigma M elementary n extension of M that satisfies T. And the proof of this again is by bookkeeping. So I looked at the proof of in Hayek and Pudlak's book that there is a full low model in settings where you consider only I sigma 1. And it seems, I mean, it all generalizes very well if we keep track of things. So nothing exciting. But as it turned out, I don't actually use this result for this the proof we're talking about right now. But anyway, it could be fun. It could be useful elsewhere. Who knows? So now to what I find even more interesting here, this version of the Uri-Hayek characterization. So this grew out of work I did with Ali when we worked on a paper that became part of my thesis later. So if we're in a setting with two sigma n plus 1 definable theories that are consistent extensions of I sigma n plus 1, where S is also pi n complete, then these three statements are equivalent. The first being that S is pi n plus 1 conservative over T. The second one being that T proves all of these bounded consistency statements for S, I mean for all natural numbers K. And the third one being that every countable model of T with S in its standard system has a sigma n elementary end extension satisfying S. So once we have this, it's going to be easy to find the desired end extension from the fact that we know that the incon statement that we're discussing is pi n plus 1 conservative over T. So we simply plug it in as S and we get the desired sigma n elementary end extension. Once we have proven this, of course. I'm going to sketch proof that the first equivalent implies the second one is more or less by the small reflection principle together with this assumption. So that's very easy. That the third equivalent implies the first is also easy. So if S is not pi n plus 1 conservative over T, then there must be some model of T plus not pi, where pi is some S provable pi n plus 1 sentence. But then any sigma n elementary extension of M that satisfies S must satisfy both pi and not pi, and it couldn't. So this was by contraposition. And the, to me, most interesting implication is the one from item number 2 to item number 3. So if we know that T proves the bounded consistency statements for S together with a true sigma n plus 1 sentences, how do we construct the sigma n elementary end extension satisfying S? So let's start by assuming that T proves all of these bounded consistency statements. And let's take a countable model M of T which has S in its standard system. So then we can overspill on K to see that M thinks that up to some non-standard C, there are no proofs of inconsistency. I mean, of something false from S together with the true sigma n plus 1 sentences up to there. So then by another result due to McAloon, we can find a submodel. Okay, so this is I think McAloon's result is only stated for M being a model of PA, so there's a refinement here that I should have mentioned. I'm sorry, but anyway, there is a submodel.
Rasmus, can I interrupt for a second?
Yes, please.
For question. So the T is M is a model of I sigma n plus 1. Is that the assumption at the beginning? M is a model of T, but T extends I sigma n plus 1?
Yes.
Okay, and so to use overspill, we have to say something about the complexity of these consistency statements. I'm sure you did at some point, but can you remind me?
Good point, good point. So this bounded consistency statement is going to be at most pi n plus 1.
Mm-hmm.
So that should be fine, right? If you have I sigma n plus 1.
Okay. I'm not seeing immediately why it's pi n plus 1.
Sorry?
Starting with S and sigma n plus 1, sigma n plus 1 truth, I'm not seeing immediately why it's pi n plus 1, but maybe I'm missing something obvious.
So let's go back. So the bounded provability predicate, I mean, this formula is pi n.
Mm-hmm.
So the consistency statement is going to be, I mean, the bounded consistency statement is going to be sigma n.
Okay. Okay.
So then we're good, right?
Yeah. Thanks.
Thank you. No, I should have pointed this out even more carefully. So thank you for doing that for me. So we could overspill to get this C, and then we can find a submodel M0 satisfying PA, which lies below this C. I'm going to draw a picture in a moment. And since we have I sigma n plus 1, we know that the sigma n plus 1 theory of M is coded in M. And we can always find a small enough non-standard code for this to lie not only below C, but also so that it's in M0. So this means that this will hopefully become even more clear when we look at the picture later. So M thinks that S plus the true sigma n plus 1 sentences are consistent up to a C. So that means that M0 living below C is going to think that everything that is in the set that is coded by A is consistent with S. So now we can use the arithmetized completeness theorem to end extend not M, but M0 to get a model K satisfying S together with all of the sentences that were coded by A, and therefore it satisfies the sigma n plus 1 theory of M. And these things being end extensions or submodels of each other, they have the same standard system. M and K are both countable. They both satisfy I sigma n plus 1. And the sigma n plus 1 theory of M is included in the sigma n plus 1 theory of K. So we can use a refinement of Friedman's embedding theorem to embed M as a sigma n elementary initial segment of K. So I'm going to show you this picture. This is our model. M, which satisfies T, plus all of these bounded consistency statements. So by the overspill we had available, we realized that M satisfies this for some C, non-standard C living up here. And then by Macaloon's result, we find this M0 satisfying PA below C, and this A that codes the sigma n theory of M inside M0. So then M0 satisfies PA together with S. I mean the consistency of S plus everything that's coded by this A. So now we end extend M0 to get K satisfying S plus the sigma n plus 1 theory of M. And there's sigma n elementary submodel I of K, which is isomorphic to M by Friedman's embedding theorem. So this is an attempt to draw some kind of picture of what's going on here. So starting from a T thinking that S together with the true sigma n plus 1 sentences have no long proofs of, have no short proofs of something false, we can construct this end extension. Okay, so with that in place, I mean, that concluded the proof of this generalization of the Ori-Hayek characterization.
Sorry, a really quick question, but M0 is depicted as an initial segment of M. Is that, I mean, it seems like that's necessary. I don't know if you, I don't know if that was, I didn't see that sort of in the statement that you, in the text that you had before. Is that what you, is that what you mean? Is this really depicted? It's supposed to be an initial segment? M0.
I certainly hope so. Yes.
I think it is. This was sort of the heart of those Macaloon's results, to get an initial segment.
Mm-hmm.
You know, you have a weaker theory that always has an initial segment that models a stronger theory. If you go down low enough, so I think the Macaloon's result is about initial segments, not just submodels.
Thank you. Thank you. Yeah, so
Yeah, that makes sense, because then you need that for the standard systems to align.
yes. Yeah, thank you for pointing that out. My mistake. So, but as an initial segment, we're good to go. So yeah, thanks again. So now we can prove that with T as stated here, every countable model of T has an sigma n elementary end extension satisfying not con of T plus the true sigma n plus 1 sentences. So let T be sigma n plus 1 definable, pi n complete, consistent, and extending I sigma n plus 1. by the previous theorem, theorem B, we know that T plus this inconsistency statement is pi n plus 1 conservative over T. So let's take a countable model of T and look at what's going on. So since T is pi n complete, then this extension of T is also pi n complete. And since T is sigma n plus 1 definable pi n complete extension of I sigma n plus 1, and M is a model of this, we're also sure that this theory T plus the inconsistency statement is in the standard system of M. So that means that the assumptions of the Ori-Hayek characterizations are satisfied. We have one of the equivalents here. We have the pi n plus 1 conservativity of this theory. So by the characterization, we get the desired end extension. Okay, I'm realizing it's 5 to 9 already, so maybe I should stop here and take questions. I think I've at least given some kind of idea about, I mean, so when we work with RE extensions of PA, some things, there are some differences that we don't see. I think that we might see a little bit more clearly when we try to disentangle things in this way. I'm not sure. It was a worthwhile experience for me to work out all of these details, but I hope some of you will find it useful too. So thank you so much.
Okay, thank you, Rasmus. So let's thank the speaker. I see some emojis already. So if you'd like to unmute, you can, or you can just, we usually do these clap emojis there. But that was great. Thank you. We have some time for questions, so I'll open up the floor to anyone. So if you want to just start talking, go ahead, or you can raise your hand.
Well, I have a mechanical question. Because, well, it's always a question one could always ask about generalizing what already has been generalized here. So this is all about definable extensions, the definable theories. So if your theory is definable, it's sigma n definable for some n, and then you have all this machinery. But how about results that are specific to a given model? And you only assume that this theory T is coded in the standard system. That's probably very weak.
Yes, I didn't look into that specifically, but I mean, you would get something for free, I suppose. So
yeah, I think it might depend on what's in that standard system, right? Because it could be, it may not contain much.
Yeah, I mean, so for example, on this slide that we're seeing, the pi n completeness of T, am I confused? No, I mean, here we're using the pi n completeness of T to make sure that T is in the standard system. So I think that you're saying that, I mean, sometimes we could do with less if we have more in the standard system or something like that.
But isn't it so that if M is a model of I sigma n plus 1, and if T is sigma n plus 1 definable, that it must be in the standard system?
Yes, that's right. I'm not sure what I was trying to say there.
Right. No, but this is probably. But there might be something interesting here if you're talking about some standard system that's small and somehow does not contain, but probably you can always find a theory that's coded in the standard system and somehow not conservative or whatever the theory of the model is. So maybe my question is not really a good one.
Yeah, I'll spend some time thinking about it at least. Thank you.
Yeah, I have a question about the role of exponentiation. So is the whole role of exponentiation to give you the truth predicates?
Yes.
So for example, if we would add the truth predicates in some sense in a primitive way, then so probably you could get below it, right? For example, S12 does interpret itself plus a sigma 1 truth predicate. So the sigma 1 truth predicate doesn't add strengths, in fact, to I sigma 1, where exponentiation does. So maybe we could think of something like that also for the other truth predicates.
Yes, that should probably work. I didn't look into those details either, but yeah. I mean, the only work that Exp is doing, I mean, that I'm using Exp for, is to make sure that I have the truth predicates and that they are enough well-behaved. So I could go weaker in the weakest cases here.
Yeah.
Other questions?
Well, I also wonder what about Rosser style arguments? Did you look at those?
No, I didn't really. I mean, in the paper, I'm really concerned with like independent formulas. I mean, or flexible formulas that they're usually described as formulas whose extensions as sets are left undetermined by the formal system. So I was interested in those, and I was generalizing that kind of results to these sigma n plus 1 definable theories. But I didn't. No, I didn't really consider Rosser constructions.
Okay, good. Thanks.
There's always something to do.
I have a question. You said something I didn't quite catch about Gaspari, and he was my doctoral student in Cambridge, so I'd be interested to know what that was.
Yes, so let's go back to where I said it. Almost there.
Quite early on when you were.
Yes. So, I mean, it's really about knowing who first showed that every model of PA has an end extension to model of PA plus not con of PA.
Yes.
And this follows from his paper on partial conservative extensions of PA. And as I think I said, I mean, the interpretability of not con PA in PA is due to Pfefferman.
Yes.
And probably Hayek or Ori or Lindström or someone should have known this.
But it's such an extremely small step from the interpretability to this result, so shouldn't one ascribe it to Pfefferman?
Yeah, maybe that's more correct than Gaspari.
Well, I'll get in touch with him and find out.
Please do. I would be very grateful.
All right.
Other questions? So I've already asked a couple, but I'll ask one more. That the version of ACT that you're using is the normal PA version, yes? Because it seemed, I mean, you mentioned this, that you were originally going to present something with sort of a maybe a version for in I sigma n or something like that, or
Yeah.
okay. So you really only need the sort of pure PA version.
Yeah, here that's enough.
That's interesting.
Since you go to this initial segment that is model of
Yeah.
PA, so you get the rest for free there. So that's a drawback of this presentation.
No. This was great. This was great.
Yeah, but instead you have to use like Friedman embeddings and finding this initial segment. So, but yeah.
Again, not a drawback. Okay. Are there other questions? Okay, let's thank Rasmus again. And I'll stop the recording.